Hello and welcome to today's presentation featuring the latest vision system from Beatty International. That's the Venture XT. Venture XT is a 300 by 300 XY stage with a full 200 millimeters of measuring range in the Z-axis. It's a 3D system, and the most important point I want to make to you today is that this is a vision system and a CMM in the same product. We've got non-contact measurement and contact measurement using the standard Renishaw TP20 touch trigger probe. So on this particular model, you can see features the optional 6-port Renishaw rack changer. The software allows us to manage multiple probes, modules, and with each module we can have a multiple stylus set up. The software is capable of understanding the calibration status of all of these styli and managing the positions of the styli without any operator influence. So when non-contact measurements required, we have our optic system here. This is a 6.5:1 zoom lens, so changing magnification is very easy. We don't have to change lenses. I can simply select the zoom position that I want to move to, and the software will take care of that as the lens is CNC controlled. Lighting on any vision system is absolutely critical. Our systems all come with our own design of LED lighting. The top light here consists of 64 LEDs, and if I turn the light control on for that now, you can see we have a graphic here that replicates the underside of that light head. These controls allow me to decide exactly how many LEDs I need on at any one point, and how bright they need to be. And also I can grab that segment and rotate it, which gives me a facility to align the angle of the light exactly perpendicular to the edge of the features that we're interested in measuring. This is absolutely key because the parts that you make have features at all angles. So being able to set lighting according to your reference and perpendicular to those features allows you to set up the system so that the edge detection can find the features accurately. In addition to that, we've got two further sources of light. We have TTL through the lens light, which is a coaxial light source that allows light to be projected through the lens itself on axis. That's great for highlighting the bottom of blind bores and that sort of feature. And then finally, we have our understage light, which is the light source that provides the silhouette of the part, the profile of the part, just like a profile projector. Our light source is collimated, just like a profile projector should be, which means that we can project the image of your 3D part accurately. So for the last 15 years or so, Beatty's Fusion software has been the software package that we've been using on all of our vision systems and profile projectors. Today we're going to talk about the latest version of Beatty Fusion, which is the V4 version, where we've got a few enhancements and efficiency improvements that I want to talk about. So let's go over to the camera and do some camera measurement. First of all, I'm just going to put this touch probe away. So, having put the probe away, we can now look at some of the camera tools that we've got available for measuring features by non-contact. Here, you can see a list of tools that I have available to me. These are all video edge detection tools, ranging from the standard geometric features like circle, line, arc, point, and so on. And we've got some more specific functions to Fusion, like thread tools, curve scanning, profile scanning tools, one-click feature, and a great new tool, which is all features in an area. So we'll come on to those later. Let's just talk about how we take data. Those of you who are used to or have had experience measuring parts using a profile projector or optical comparator will be familiar with this. You would typically, in the most basic form, use the crosshair on your screen to target points. And I've got a crosshair here on my screen, and basically I can simply zero out the DRO count. We can move the object across, the image across, align that with the crosshair and read off a distance on our DRO. Simple point-to-point measurement. Of course we can still do those simple, quick and easy measurements on the Venture, but for the most part we're going to change our measurement method from crosshair and any of these other manual methods to edge detection. That's the power of vision. So when we take edge detection measurements, I'm just going to line this part up so that we can start to show you the difference. So with using the video edge detection tools, I can simply draw a box over the edge of this line that I want to measure, and I'm creating a scanning width here, and with the next click of a mouse I've fired the tool, and you can see here that I've taken, in this case, 233 points in one mouse click. So the first thing that you can understand from that little exercise is vision's fast. So if that was the end of this feature, I would simply hit the green tick and we would move on to the next feature, but I can see there's more of this line outside of my current field of view, so I'm simply going to either use the joystick or the mouse to drive the stage over and fire the tool again. Because my measurement window is open, I can simply add more and more data, measuring bigger features using multiple camera grabs. So I've measured a line now with 430 data points. I'm going to use that as a reference feature, an alignment feature, and that's the end of that. And you can see in my XY view here now, I've actually drawn the feature we've just measured. Let's bring a circle into view now. Same thing, I haven't changed the tool because I've got an auto select tool selected up there in my toolbar, and you can see that tool just automatically went to a circle tool. Same process, I've got a scanning width here, and in this case I've scanned a nominally 2mm diameter, taking 304 data points. So what that tells me is a very accurate calculation of that diameter, and here it is, but it also gives me a very, very good understanding of the form of that circle, because 300 and something points around a 2mm circle describes the shape of that circle extremely well. So it's like we've scanned it, and vision gives you a good understanding of form error as well as the nominal geometric result. Okay, so a great tool that we have on the Venture XT is the ability to drive the stage using the mouse. So if I just click my mouse and grab the image and drag it across there, you can see that the stage does a corresponding move. I don't have to take my hand from the mouse onto the joystick to do that, and that's a really convenient way of driving the machine around the part that you want to measure. So again, using the auto select tool, I'm simply drawing boxes, and you'll notice this time I'm speeding things up using the mouse drag tool. I'm not even having to complete each of these measurements, I'm just simply drawing boxes. The software is making great decisions about giving me the right kind of tool for each feature. So for simple parts like this, setting the inspection routine up is incredibly easy. If you can use a mouse, you can use Venture. So having created some measurements using our video edge detection tools, you can see here on the left hand monitor I've got a graphic representation of the part we've just measured. So clearly we've measured something, but where are the results? Well, the way that Fusion works is to just simply allow you to select the features you're interested in and start to populate this view with dimensions, just like that. So if I want the angle between these two lines, I'll simply select those two lines, and the software intuitively gives me the right dimension type according to the selection I've made. Now, a lot of people like this style of reporting. As engineers, we're all used to reading engineering drawings, so basically I'm arranging this view just like the drawing, the manufacturing drawing that I'm using to control this part. So another example would be if we selected, say, this radius and this radius, the software's previewing the dimension type it's going to give me, and if that's the way the drawing calls that out, then that's fine. I'll just decide where to position that dimension. But if it's not, then simply right-clicking at this point allows me to change the dimension type to the type that replicates the way it's called out on the drawing. So setting up your results in a familiar way is incredibly easy. So, having measured standard geometry using our geometric tools here, I'm going to show you some other tools that we have in the video edge detection range. The next tool I'm going to show you is the curve tool, which is a profile scanning tool. So here I have a shape which is all within my field of view, and to describe that shape with data points, I simply set a start point, set a scanning direction and an end point, and you can see that the software completely scanned that outside shape. In this case I took 485 data points. I could have taken more or less according to the application requirements. That's a user definable setup. Let's OK that, and you can see now in the middle of my shape I've got a point cloud describing that shape. Let's go for a bigger shape now, using the mouse drag tool again to drive the machine. Let's start here and ask the software to search in this direction and keep going around that part until it's actually described the entire shape. This time the shape is much bigger than the field of view, so the system's having to follow that shape and use the CNC control to actually navigate its way around the entire part. Now, I haven't had to program that, I haven't had to do anything, just give it a start point and an end point that's the same. And now we've got a 2000 data point cloud describing the entire shape. That's a great way of comparing profiles to imported DXFs, thread forms, all sorts of complex shapes that would be almost impossible to describe by combinations of blended radii and other standard geometry. So scanning and best fitting combined with standard geometric measurements is very, very easy to do in the same inspection. So, having used the curve profile scanning tool to create this point cloud, what are we going to do with that data? Well, the most convenient way of using that data, I think, is to import a DXF file so that we can compare the data to the CAD profile and see how close it is to the nominal profile. Profile projector users would relate to this in terms of an overlay, the transparency that you would actually place onto the optical comparator to try and find a fit between the projected image and your drawn image. The DXF is basically an electronic version of that. So let's bring in a DXF of that shape. I've found the file. I'm going to import that file as a curve profile. We can use DXFs for other purposes, which I'll cover in other clips. So we're going to bring this in as a metric DXF. I'm going to apply a 0.2 tolerance band as a general tolerance band to this DXF, which I can edit later. And let's bring in the DXF, and you can see here the initial position is slightly off from the measured position. So we need to do some manipulation. Just like you would do with the profile projector, you'd manually move that overlay chart around to try and visually align that with the image. We can do that also using these controls. So I'm going to jog the DXF to the left, to the right, up and down, and I can also rotate it, but clearly what I want to happen is for the software to calculate the best fit. So by pressing the start button there, the software does a calculation and has mathematically fitted the DXF so that the profile error is actually minimized. This is the best profile error. And you can see that all of my data points now have gone green and are showing as very close to the nominal line. So visually, I can immediately see that all of those green data points mean that every one of those 2.5 or something thousand data points are within the 0.2 tolerance band that I imported with the DXF. So that is a visual equivalent of the profile projector overlay. Okay, so having brought the DXF in and made a best fit calculation, we get this visual report that all points are in tolerance. That's great. The problem with camera-based systems in the past has been the limited field of view means that we can't see what that overlay and image fit looks like. The big advantage with the latest generation of Fusion software is that we can stitch our images together. This is my current camera view, but if I roll out on the mouse and zoom out here, we can see that actually I have a picture of the entire part that I've measured, because every time we've been to a position, we've saved that image and connected them all together, stitched them all together to give us a larger saved image. Now, on top of that image, I can use this feature, overlays, to show other information on top of the stitched image. If I select DXF, you can see I can bring in the DXF here, and I can see that all of the features now fall within my tolerance band. So this is the view that we're used to seeing on a 500mm screen profile projector, and now for the first time we can actually replicate that on a camera-based vision system. So now we have a visual graphical display showing our points, our scanned data points as green and in tolerance. We also have a visual overlay of the DXF placed over the top of the stitched image. So anything, even if we haven't measured the feature, we can still see where it appears in relation to the DXF. But the final thing that a software-based system like this can give you is an actual result. If we want to, we can dimension that profile and actually put a number on it. And that's the massive difference between this subjective view that you have to take with a profile projector and using this method where we can automate the process. We can visually see all of the things that the operator is used to seeing, but at the end of the day we have a number that we can report. We have empirical data that we can report, we can tolerance, and we can plot trends. That's where the industry needs to be going. So the process that we've just been through, using video edge detection tools to automatically find the edge of features. We've taken lots of data points to describe all these features. We've created a drawing. We've dimensioned the part. We've done some scanning and best fitting to DXFs. At the end of the process, we've generated a report, but the real value in the system is that it's a CNC system. So if I hit the play button now, you'll see that the software has actually remembered everything that I've done. We've got a program to measure this part now, and that is what we call the teach and repeat programming style of this software. I'm not actually having to program anything. I haven't touched the keyboard yet this morning, yet we've created drawings and reports and we're measuring a part automatically. Okay, so we've used the video edge detection tools, the camera-based measurement tools for measuring features and scanning profiles, comparing to DXFs. Let's talk now a little bit about the CMM side of the machine. Standard Renishaw TP20 module is mounted there. I'm in the middle of building some probes for that. Beatty Fusion V4 software manages probes incredibly well. It makes it very easy for the user to build probe sets and new modules. I'm just going to add the final stylus to this particular probe set, and if I go up to my probe manager here, I'm just going to add the X Plus stylus. I've got a 2x20mm stylus mounted, so let's add that, and simply a case of making that the current stylus and then asking the software, asking the machine to go and datum itself. So the machine's now driving that stylus into the reference ball. The system obviously knows where the reference ball position is, and using that information we can not only calibrate and calculate the stylus tip diameter very accurately, we can also calibrate and calculate the tip position relative to the other tips and the camera. So having done this process now, I can select any of the tools in my probe library, and any dimensions that I make with any of those tools can all be related to each other because the offsets are known. So, having calibrated all of the probe tips that I have assembled on this TP20 module, I can now use the little graphical icon that I've got here, which shows each of the tips that are assembled, and it's just a question of clicking on the tip that I want to use for the next measurement. I'm going to click on the Z down tip, that goes green, and now we can call for a plane measurement, and we're going to use touch probing to measure some of the features on this machined aluminium part. So let's move over, and I'm going to bring the touch probe in close proximity to the surface to measure this plane, and then using a joystick gesture there, I can ask the software to control that probe approach so that all of my probe measurements are taken under control speed and I'm not influencing that speed. So even as a manual measurement, I'm able to drive the probe using CNC control, like so. So let's take 4 points on a plane to describe the top surface of that component. We'll use that as a reference feature, and we're starting to draw the features in the X, Y and in the 3 views, just like we did with vision. So now let's measure a circle. I'm going to call for a circle measurement form, drive the touch probe into the bore, and using the joystick control I can ensure that probe points are taken at a controlled speed, so I'm not influencing the probing speed of this of these measurements. I'm just driving somewhere close and asking the machine to finish the job for me. So there's my diameter. We'll call that a reference feature for this template, and let's come out of there. And now I'm going to change tip, and we'll select the one of the X-axis tips and measure some features on this face. So next let's measure a line. I'm going to use a different tip to do this because I want to use a line on the side of this component, so I'm just going to use the graphic I referred to earlier. Let's click on the X-axis stylus and just drive down. I'm going to measure a line, so let's come somewhere close, call up for a line measurement, and again just flick the joystick towards the part, and the part is measured using controlled probing speed. So again, I'm not influencing that measurement. So that aligns the part, and now let's measure some other features on this side face. Let's call for a plane, and we'll first of all measure the plane around this bore. And now we can see some of the more three-dimensional views coming into play. So, as you can see, we've measured quite a few features now using various tips on the currently mounted TP20 module. The next thing I want to measure is the O-ring groove that's in the top of this housing. It's a very shallow groove, so I'm not going to be able to measure that with any touch probe. We don't have one small enough. Great example of why the Venture is such a great solution. We can just simply employ the camera now instead of having to take this part off the CMM and move it over to another measurement method. So let's put this probe away because the length of the probe is such that it would actually foul on the part. So I'm just going to ask the software to put that away. And having done that, the software automatically gives me the camera as the active probe now, so I'm ready to go measure with the camera. So now let's measure this groove diameter and width using the camera. I've got an arc tool selected here, so I'm simply going to scan the edge there, having already organised the lighting to highlight that feature. So let's move around and adjust the lighting, and you can see the effect that the lighting has. There's a great edge there, so we'll use that lighting condition for this grab and move around the diameter. So having taken data grabs all the way around this groove diameter using the arc tool, different lighting conditions for each grab, all of that's getting automatically recorded into the program, in addition to all of the touch probe measurements that we did, making the finished article a combination of contact and non-contact measurements on the same inspection. All completely automated and couldn't be easier to use. Okay, so let's run the program. So the software knows that it has to first go and pick up the module, and we're going to use each of the tips that I selected to measure the various features. Okay, so having run the program, we can then look at the results that we've got in the form of several reports. You can see here, if I open the report manager, we've got a number of reports available to us. Graphic details, tabulated dimensions, and also reports that cover multiple components when a batch of components have been run in the same automated process. So let's look at graphic details. I can choose which view I want to display. This is the XY view, and all of the dimensions that are associated with that view are reported here. So taking a look at some of the other reports we have, tabulated dimensions is a much more conventional looking report, spreadsheet style. Lists out all of the details for each of the dimensions, including the nominal, actual, the error, what the limits were, and whether that result was classified as a pass or fail. The same information that I typed in to form the drawing border on the graphic details report now rolls through into all of the subsequent reports, so I'm not re-entering that data. In this case, it forms the header. So the file format for this report is already XLS compatible, so as soon as you email that report to a customer, or you want to use that internally in the company, that's in a file format that you can readily open and review and edit. Moving on, we have a multiple components report. This report summarizes the feature results for each component in a batch of components. So if I have a batch of 20 components, we can look at the individual report for each of those components, and we can also see a summary of the whole batch of 20, and if the whole thing's passed, then we have one summary report on a single page. Very useful for production batch work. And finally, if we look at SPC, SPC data is also collected in our software. We have very good SPC capability included as standard in the software, and you can see here I've picked one of the dimensions, and we've got a normal distribution chart here, and here's our X-bar chart for this particular dimension measured over 9 components. Control limits are calculated automatically, and all of the statistical summary information is listed here. Again, that's Excel compatible. Finally, another option for reporting data is to actually send that data out of our software in a CSV file format, so that it's possible for you to import the data into other proprietary software that you might be using. I can show you a preview of that. Here is a CSV output of the report that we just reviewed. In this case, I've chosen to include the headers, which is an option, and here are all the results in a comma separated value, so that that's easy to import to any proprietary software that you choose.